functions are actually implemented in hardware. And we start with gates. Yeah, you love gates. Yeah. Bill Gates or some other gates or just digital gates. All right. Gate is a digital logic circuit. So that is, it's an electronic circuit, all right? We are not, things might be very different with quantum computing, but for now, all the hardware we have is based on electrons, so we call them electronic circuits, and so we call logical circuit a graphical representation of some electric circuit that performs certain function. So initially, we'll be mostly dealing with Boolean functions. So we have to look at how those operations that we discussed and or not are represented and how we can combine them as electronic hardware devices. Okay, so a circuit is built up of gates and other components, other electronic components. We just start with gates, and then things will get more interesting because we can have, we can combine those gates into combinational circuits and build a lot more complicated stuff. So each gate implements some simple logic function. All right, and here it is important to kind of abstract from the real implementation in hardware, right? So we not going to be going down to the level of transistors and actually discussing how, from the electrical engineering perspective, those functions are implemented. Okay, that would be the next level, but that clearly would be out of the scope of this class, right? It would really be an ECSE topic more than it would be a computer science topic. So, the level of exposure we get is those graphical representations of gates. Okay, they still correspond to, like, if you want to implement then this circuit in hardware, you would first have to draw this circuit diagram or schematic diagram using those, boxes, so to speak, to represent certain functions. And then you would, probably select chips, or most likely it will be some programmable device these days that would implement this function using their actual transistors and gates and all that stuff. Okay, so we're not gonna go that deep. We're only gonna go up to building, drawing circuit diagrams. All right, and there's a question: can we draw on paper and scan into our typed work for homework 4? The answer is no, and it will be described in the rules of homework 4. We will ask you to do everything in open circuits. Okay, and you will actually need to take a picture to include in your PDF file, and that is easily done in open circuits, but you will also need to give us the open circuits file so that we could actually run your circuit. Okay? Yeah, so you will be submitting circuit files. Not on the exam, of course. On the exam, because the exam is pen and paper, you just draw and that's it. But on the homework assignment, you will need to submit the actual files, and we will describe how this is done. Yes, you will do a lot of hands-on stuff with gates, right? Okay, so for us, because we agree that we're not going to discuss how this gate is implemented using the transistors. So we will just draw it as a box of a type, and then assume that this box implements the function that we need. So in the most general way, a gate, right, where we say a gate implements some Boolean function if it's a function of two variables. So the inputs are the variables, the arguments. Okay, so their inputs are traditionally shown on the left of the box, and then this box corresponds for the hardware that performs a certain function. So if a function is AND, it will perform this AND function and Boolean function on two Boolean arguments, and then the output is shown on the right and that's the output. That's the function that is being computed. So it's important to see that, whatever is inside doesn't really matter, but we assume that their output is tracking the inputs, and the output always reflects the state the state the states of the state of the inputs. Okay, so you don't have to kind of recompute or refresh. The output reflects the state of their inputs. So, and it's the easiest form of circuit, and it's called a combinational circuits because it has no memory, right? It just the output is directly straightforward in a straightforward manner the function of the inputs. All right, so gates compute something, right? That's important. That's why we're talking about gates, because we want to learn how computers actually compute, right? So how is computer able to do a plus b, 5 plus 7? How that actually is done, right? So, and the first thing that we mentioned is the output depends on the inputs. The output is a function of the inputs. The output tracks the inputs. If any of the inputs changes, the output might change to reflect the change of the inputs. Okay, and if the inputs do not change, it is guaranteed that the output does not change. Again, this is for this simplest form of circuits that we call combinational circuits. All right. So, and now the important thing is their notation. So to distinguish between those boxes, we use slightly different shapes for them. So this is the shape for an OR gate, right? And so the inputs are on the left, their output is on the right. So this is the OR gate, and this is an AND gate, so that we can visually easily distinguish between the different types of gates. And this is a NOT gate, or negation or inversion. Okay, so those are three gates that we have, and here is their notation, the graphical representation for NAND and NOR gates. So you see, it's actually a kind of we can just superimpose and not, or and not, right? So what we and you can read this very easily because the basic shape is that of an AND gate, but then we have this circle here that stands for negation. Note how this is the same circuit here, the same circle here. Okay, so that basically says, well, do A and B first, and then negate the result. And that is exactly what NAND gate does, and the same for NOR. Okay, so you can, you really need to remember there are two basic shapes. The AND, has this straight side here, and the OR has this curvy side here. Okay, and then you can combine it with this circle here, which would just mean we want to negate the result. All right, so combinational circuits, we can put gates together into circuits. So we can combine, now that we have those basic gates, we can start using them as as bricks to build larger circuits. And our circuits, if we use those basic gates, no memory, then they would be just combinational circuits, which means that the output is a function of the inputs. Okay, so if the input changes, the output changes. And we can design circuits that represent any Boolean function. So let's actually do something. And let me discard all changes. And yeah, so please feel free to follow along with me to the open circuits. So here is the URL. And yeah, open circuits is actually an RPI Argus project. So this is their GitHub. So it was this project started at RPI. Yeah, thank you for someone putting the link in the chat. Good job. All right. So It's an Argus project, so it means it's just a bunch of students taking Argus class at RPI, decided to do this cool, cool system that they called open circuits to, to allow people to draw simple digital circuits and then kind of simulate their behavior. All right, so it's a great learning tool. It's not the only tool, and actually previously in this class we used another system that I will mention because maybe for some of the more advanced stuff we would have to use it. So this other system is called Logically. Okay, that's what we used before, and they have a free trial, which I was just using in the browser, so like that. Okay, so it's a little bit more advanced, but for at least for all the basic stuff, we're going to be using open circuits. All right, so I want to pay my dues to their people, and they have a big team. It's like over 20 people actively working on open circuits now this semester too in Arcus class, so they are making improvements daily. Okay, and they're actively developing their system, and they're doing a great job. So I want to pay my dues to the team of open circuits and use open circuits for anywhere I can. And if I come across something that open circuits cannot yet do, I might have to resort to logically. Okay, but I will try to stay with open circuits. Yeah, and of course, and when I asked Leon, who is the project lead of Open Circuits, like what was their largest number of users they had at the same time using Open Circuits, they actually didn't. They actually did not know. So if we see that there are any problems with 200 people accessing Open Circuits at the same time, if we if we see any other bugs, of course, their requirement to submit circuits made with open circuits will be lifted. Okay, of course, we know, we are trying to stay aware of any problems, and of course we don't want you to be responsible for something that is beyond your control. Okay, so I'm keeping my fingers crossed. Open circuits behaves well, and we all use it and enjoy it. But if something goes wrong, of course we will adjust the requirements. And they recommend that we use nightly version because it has more features. I don't think the stuff that we, at least initially for the first, few lectures, I don't think we're going to use anything advanced. But, so you may try using, the stable build open circuits IO, not nightly open circuits. All right. So let's actually try drawing something. All right. So here, and you can see my open circuits window, right? Okay, cool. All right. So we want, let's say, to have an AND and a NOT, and combine them. And I want to have an AND and two NOTs. Wired like that. And I want to have an OR wired like that. Okay, yeah, I need an input. So for the inputs, we can use either constants, 0 or 1, or we can use those switches or buttons. So let me use the switches, and I will wire my switch to all the inputs that I have. Okay. And we want to observe the output, which is, I like this LED thing. For something more advanced, we might use those displays, but for just Boolean stuff, this is fine. All right. So I just built a very simple combinational circuit. Why is it called combinational? Because its output depends purely on their inputs and nothing else. Okay, so if I don't change anything, my LEDs do not change, right? These two are lit, their bottom one is not lit, and it's going to stay like that unless I start changing the switch. Unless I start toggling the switch. So if I toggle the switch, you see how the color of the wires actually indicates their high or low level, true or false. It makes it easier to debug. So you see that now these two LEDs are lit and this middle one is not lit. Okay. All right. And clearly it is a combinational circuit. Okay. Note that the middle LED does not change as I flip the switch. So an output does not have to change when I change the inputs, but it may change. Okay, that's the important thing to remember about combinational circuits. All right, so and what do you do with, imagine this is the circuit that you need for your homework. So how do you download it? So you first and you can download it. So this is the most important thing. You can download it as a file. So, and it's going to be a circuit file, a circuit. So in folder, and you can see it's just this dot circuit. Okay, so when we ask you to submit your circuit as a file for the homework, you just submit the circuit file, and you would have to rename it because we tell you how to name the file. So it would be something like homework 4 circuit. Maybe there will be more than one circuit, so we will tell you how to name the files. Okay. So yes, homework 4 will contain circuits for sure. Okay. All right, and then if you need to do a screenshot for your PDF, all right, so we ask you not just to submit the circuit file, but also to take a screenshot and include it in your PDF. So this feature, I was told, does not currently work. Yes, and it still doesn't work, so maybe they will implement it shortly, but it's not a problem because you can always take just a screenshot and something like that. And so as you can see, it's if you save it here, okay, it's just a screenshot, okay, and you just include it in your PDF. All right, so that's it, and let's look at now the actual circuit that I tried to do here. So this upper one is AND with a NOT. Okay, so it's a NAND, and I can verify that it is a NAND. Right, if I use this, wire the same inputs, and look at their output. And as you can see, I'm learning this along with you. I don't remember how to pan. Okay, I got it. It's a middle mouse button. All right. So, and if I flip my switches, I see that, well, no matter what I do, my two upper LEDs are exactly the same. Okay, but to verify that they actually perform the same function, you have to check all combinations of inputs, all four of them. So if I start with everything turned off, 0 and 0, okay, and so you can have a label here, right? So you can say if I don't like this, you can say label A. So input A, input B, okay, so something like that. So please, in the homework, you will need to label everything, okay, but this requirement will be spelled out. And so we start with both A and B at 0, then B goes 1. We see that these two LEDs are still showing the same value. It doesn't matter which value, right? If we are just trying to establish that, these two circuits implement the same Boolean function, we just care that they are the same for all combinations of inputs. So, and then we try this, they're the same, and then the fourth combination, 1 and 1, we see that they are off. Okay, so that's how we can see that this single NAND gate performs the same function as AND followed by a NOT, quite predictably. Okay, and now let's look at this part here. Okay, so we first invert A and B, and then we route it to their AND gate. All right, so if I want to put a label here, what is the function that this part of the circuit implements? All right, so, and I can write it A, and I don't know if there's a dot here, but let me use asterisks for now. Okay, so this is not A and not B. Okay, all right, so what about this? This is simply A or B. Okay, all right, so now I want to implement come on. This. Okay. So, and to do that, I need an OR and a NOT. And I use the same inputs. Of course, you don't have to. You can, use different inputs. I just want to make sure that all my, sub-circuits use the same inputs for now. And then I need the LED. And actually, let's use something else. Let's use the BCD display just for fun. All right. No, I don't think I wired it properly, so let me rewire it. Yeah. All right. So, and you can see that it, with this BCD display, you can actually show 0 or 1, in this form. Okay. Yeah, you can also color them. Yeah. Here's the color. All right, so now my question to you, please help me implement the same function, but using the AND gate. So I want the same function as this one, but using an AND gate. So as I'm wiring the inputs, please let me know what I need to do. De Morgan, exactly. So which additional components do I need? Let's say I cannot use OR gates. All right, I need 2 NOTs. Where do I put 2 NOTs? Exactly, so I need to I need to negate my inputs, and actually I'm going to reuse the NOTs that I already have, okay? So this is another thing. If you already have some output that performs the function that you need, you don't have to repeat it. You can just reuse the same output again. In the logical circuit, it is perfectly allowed. In a real electrical engineering design, you would have to be concerned about the load, because every integrated circuit, every actual electronic device has a loading capacity, so you cannot connect infinitely many loads into any output. So there is a drawing current max capacity, but for logical design we just ignore it, so you can connect as many you know use a particular output as many times as you want. Okay, all right, so that's that. And let me do the BCD again. All right, and now let's verify that these two actually perform the same function. All right, and so I can leave it like that, because the formula would be different, but if it's the same function, it doesn't matter which formula I use to express this function, right? So, but let me type it like that. Not A times not B. Okay. Right, so they are both at, and let's start with both zeros. So their output is both, for both of them, is at 1. I flip both zeros. I flip both zeros and both zeros. Okay, so I clearly see that for all combinations of inputs, the output of these two circuits, they match, which means they implement the same function. Okay, yeah, and yeah, you don't have to the logic gates that are available to you, you can just use them. You don't really have to build them from multiple gates, but you can. So it's important to see that this NAND is nothing more than AND followed by a NOT. Okay, and you can actually, one other thing that you can change is the number of inputs. So you can have gates that have more than 2 inputs, because you can have functions that take more than 2 arguments. Okay, so that is totally possible. So will next week's exam be like half MIPS, half Boolean algebra? Yes. There will definitely be MIPS with procedures and array and saving stack and saving S's and T's. So everything that we discussed last lecture, and there will be definitely this material on Boolean algebra and circuits and that kind of stuff. All right. So yeah, we'll see how far we go today. All right. So and we just built similar circuits, right? So this is another example, right? And here is their question. That's our next pop quiz. What is the output? Which formula expresses their function computed by this logic circuit? And let me open. So I believe this is our poll number 3. Okay. So hopefully it's the right one. And we are moving on. All right. So we now have the third. We just discussed the third way to define a Boolean function. Okay. So it's a circuit. So we can give you a circuit, and that circuit would define some Boolean function. We can give you the equation like A plus B, A or B, or we can give you the truth table. They are all different ways to define a Boolean function. All right, and implementation would be exactly the logic diagram that we have seen. So you just grab the gates and connect them, wire them up, and yeah, that's it. So in a real electronic circuit, electronic device, you would also need to take care about the power supply and a bunch of other stuff that electrical engineering is concerned about to actually make this circuit work, right? But for the logic design, don't worry about the power source. We assume that power is given to us by some magic being, and we don't have to worry about it. Yeah, infinite power, exactly. All right, so integrated circuits are actually, the simplistic view is just it's a bunch of gates packaged together. And a long, long time ago, in a galaxy far away, you could actually buy their ICs, the integrated circuits or chips that would contain things like that. Like, this picture here is a real chip that is probably 40 years old now, and it's no longer used because it's just too low, low level of integration. It's you know that there are a lot more powerful chips now that contain probably millions of those gates. Okay, and so it's no longer used, but it's a convenient model to look at, and it's a real thing, right? So like 40 years ago you would actually buy those chips, and they would contain like those four end gates, and then you would just build your entire circuit from that. And of course you would have to for any realistic, any more or less complicated device, you would have to use hundreds, thousands of those chips, and you would have multiple PCBs, multiple boards, and stuff like that. So these days, of course, the integration level is much higher. So you can basically buy one chip with multiple many pins. In many cases, several hundred of pins, and then actually program that chip to implement the function that you want. So we are in the era of programmable chips, right? So you have to write software to actually program a chip. So there's more languages for that. And if you read your textbook, then this language, one of those languages, one of the most popular languages for doing that, for programming, for writing programs for chips, is actually described in our textbook. It's called Verilog, and we are not going to cover it in this course. It's very exciting. It's thrilling, but that would be too much for this course. But if you're interested, please please read it. And while since I mentioned that, let me point you to something else. All right. So here in our course materials, I posted under reference materials. So I posted a bunch of PDFs that are additional additional material for our textbook. So our textbook only the print version only contains some core material, and the authors made additional material available to anyone for free. So even if you didn't buy the textbook, well, I know all of you did buy the textbook because it's required for this class, but even if you didn't buy the textbook, you could go to what is called a companion site for the textbook and download those PDFs. So those PDFs are not copyright protected because they are not in the print textbook. They are just additional material that authors didn't want to include in the printed textbook, but wanted to make available to everyone. All right, so those please read through those, and one of them is this Verilog tutorial. So if you read one of their in one of the appendices, I think it's appendix A, the A or B, probably A. Right, there's a chapter on there's material on Verilog, and then there is this tutorial on Verilog. So if you feel interested in that topic, please take a look. It's exciting. All right, and we are back to here. All right. And we just talked about implementing Boolean functions. So Boolean function can be expressed as a formula, as a circuit, as a truth table, and we can actually come up with different implementations of the same function. And we just saw that in open circuits in the examples that we've done. So, and we've seen that it is actually possible to implement the same function using different number of gates, depending on, it's kind of equivalent to, if you start with a formula, you can, let's say you have a formula, you have a Boolean expression that uses 5 pluses and 10 dots, and that would correspond to the number of gates that you need to use to implement this formula in a straightforward manner. Just one to one from their Boolean formula, from their expression. But then it turns out that maybe by applying some Boolean algebra laws, you can simplify this expression so that it uses fewer operations, fewer pluses, fewer dots. And that, of course, if you transform this expression into a simpler form with fewer operations, and then you implement this formula instead of the original formula, you're gonna need fewer gates. And of course, this is desirable, right? This is good. We want to spend as little money on our gates. Imagine you have to byte each of those gates. Imagine that you have to pay for each of those gates. So of course, we want to minimize the number of gates. All right. So here is an example, and we have this this formula here, okay, which is a times not b, a and not b, or not a and b. Okay, and then we compute this this function given by this formula. So it would use 3 gates, right? We're going to need 1 OR and 2 AND gates, and yeah, if we build the truth table, we realize, oh, this is really an XOR function. So we have a gate, just one single gate that can get us this same function. So instead of using 3 gates, we can use just 1 gate. Okay, of course it's easier. It's less hardware. Okay, so this is one implementation, just straightforward implementation of our formula, right? We have to have negated A and B, so hence our 2 inverters here. So the NOT gate is also known as an inverter because it inverts the value, and then 2 ANDs and then an OR here. Just straightforward from the formula, right? And here is another implementation of that. Okay, so how many gates do we have here? So we have 2 AND, 1 OR, and 2 NOTs. So we have 2 NOTs, 2 ORs, and 1 AND. So it's slightly different, but in terms of the number of gates, it's the same. So you see that we just applied one of their laws, one of the transformations to switch it from this form where our function is the sum of products, right? Because we can treat this as a sum, as a Boolean sum, and dot as a product, from the sum of products into the product of sums. And we didn't gain anything in terms of the number of gates, but it's a very interesting observation that will be important. All right. And to prove that it's actually the same function, right, we have to do some work. And here's how you do it. So please review that. For every step, we specify which law or which postulate we use. So each step, and when we ask you in the homework to prove something is the same function as something else, that's how you do it. So every step you have to explain what you do, right? You cannot just eliminate stuff or perform some combine 2 or 3 steps into one. You have to spell out, you have to justify each step by specifying which law you used. Okay. All right, and then logic design. So, we just talked about simple components, but we can also come up with some hardware that is very useful in processor design. So you can build everything from those simple gates, but there are components that have more complicated functions, and we oftentimes want to just talk once about how this more complicated device is built, and then represent it with just a box. Okay, and that box inside will contain all those gates, maybe dozens of them, maybe hundreds of them. But we want to, once we discuss how this is done, we want to abstract from the implementation of that particular component and just use it as a black box, as a component that performs the function that we need. Okay, so we will use those components when we design control systems later. We will build our own processor. Okay, so just a heads up, it's coming up. All right, so let's look at their components, at some of their components that we need to build our processor. And this stuff is extremely important because later on, our next topic in a couple of weeks, maybe less, is actually looking at the design of the processor. And you will have this big diagram, okay, that will be using the components that we are discussing now. So if you do not understand the material that we talk about now, you will be definitely unable to understand the data path diagrams, the diagrams that show the internals of the processor, because it will be using the components that we discuss now. Okay, so it's extremely important to understand this stuff now. Yeah, it's a little bit of computer engineering. I agree, but it's useful for all computer science. And I believe, of course, you're free to disagree, but I believe it is useful for all computer science people to at least know how this is done. Okay, we will not be asking you to build, a more or less complicated processor or a real world processor from scratch. Okay, that would be too much. But you need to understand how processors work and how, because that answers the question how computers compute, how this is actually done. All right, so first components that we talk about are decoders and multiplexers. So both are important, but multiplexers are especially important. They are you're gonna see a lot of multiplexers, okay, in the future lectures. All right, so let's start with decoders. A decoder has n inputs and two n outputs, and the function that the decoder implements is the inputs are used to select which one single output is turned on. So only one of the outputs will be activated, will be at true or 1, and exactly which one is determined by their inputs. So we have n inputs. Essentially, they encode their output that should be activated. So you can treat those n inputs as an n-bit number, and the output with that number will be activated, will be true, will be at 1. Okay, that's why it is called decoder, because it takes encoded number with n inputs and it decodes it so that it activates only one of the outputs. For multiplexers, and no, the multiplexer is not the opposite of a decoder. So, the opposite of a decoder would be an encoder that has two n inputs and n outputs. Okay, so it's also a component that is used, probably not as much, but it is a useful component. That would be the opposite of a decoder. Multiplexer is a component that basically allows you to route an input to the output. So multiplexers have two n inputs, 2 to the power of n inputs, and selection bits. So those selection bits are also inputs, and one output. So selection bits select which of the inputs is connected to the output, is routed to the output. Okay, and this is a very, very important component because if you think about it, it's like a programmable switch, right? So you change those selection bits and they rewire their input to the output, right? So they rewire which input gets connected to the output. All right, so this is a decoder, right? So two inputs, which means that there are 2 to the power of n outputs, so 4 outputs, and this is the truth table of a decoder. Okay, so as any combinational circuit, you can express it with a truth table, right? In this case, it's just 4 functions at once, O0, O1, O2, O3, and two inputs. Okay, so, and the way it works is if you look at the inputs as the number, so, and it's binary, so it's 1 and 1, which is 3. It means that O3 will be 1 and all other outputs would be 0. If my inputs change, and let's say my inputs are now 0 and 0, then 0 and 0 is 0, so it's number 0. So it means that 0 output, O0 or not, will be activated, will be 1, and all other outputs would be 0. Okay, so you see how decoder actually decodes their number from basically their binary form into one output wire, one output that will be activated that corresponds to that number. Okay. All right, and this is the truth table. So you see for when both inputs are zeros or not is 1, the rest are zeros. And note how if you look at any column, okay, only one input, only one output is activated. O1, O2, O3, only one. The rest are all the remaining 3 are all zeros. Okay, that's their rule. That's how the decoder works. Okay, and then from this truth table, we can build their formulas for each of the outputs. Okay, so remember, their circuit, their truth table, and the formulas are 3 different ways to express a Boolean function, and you should be able to use any of them as the input and then produce the output. So if we gave you the truth table or the circuit, you should be able to come up with the formulas, because quite often with the formulas you can do your Boolean algebra laws and maybe simplify those formulas. We shall see how this is done. So, and here we had this decoder as a black box, but it can be implemented using gates, because once we've written our expressions, our formulas using and, or, and negation, we can actually build our decoder with our basic gates. And this is exactly the decoder. Okay, and you can just look at any one of their outputs. Okay, so it would be not I0, not I1, ANDed together. And this is exactly what happens. We have an AND, which takes a negated I1, negated I0, and ANDs them. That's the definition of O0 or not. All right, and of course we can have decoders with more inputs. So with 3 inputs, the decoder would have 2 to the third 8 outputs. And that would be the truth table of that decoder. Again, the same principle applies. Only one output is activated at any moment of time. All other, we also say in electrical engineering, setting something to one set, we say assert, right? So O0 is asserted here, and all other outputs are deasserted, okay, or are not asserted. So it means they are at 0. All right, and here are the corresponding Boolean expressions. How to get Boolean expression? Just from this truth table, okay? So this is the logical kind of progression, and then that's how you implement your 3 input decoder or 3 decoder. And it's only partial implementation for only 2 outputs, but you should be able to implement the rest of them, O2 through O7, by just looking at those formulas and selecting the proper gates. I highly encourage you to actually do this in open circuits, just to get the practice, and then make this circuit, make this 3 decoder from basic gates and, or, and not, and then connect switches to I0, I1, I2, connect your LEDs or the BCD display to the outputs, and flip the switches and see how outputs change, how outputs behave. All right, so we can also perform a useful simplification that I mentioned. If you have this, all right, you don't have to use 2 AND gates. You can use one single gate with more than 2 inputs. All right, so you can use 3 inputs, a 3 input AND gate as in this example, and I showed you before how to do this in open circuits. You just put 3 instead of 2, or whatever the number of inputs you need. All right, and with that simplification, if you have access to 3 input gates, you can build your 3 decoder in fewer gates. Okay, so let's stop here at slide 60, and then we will pick up from here on Tuesday. So thank you, everyone. And yeah, we had very few questions in the Q&A this time. So maybe we need to reduce the number of panelists because otherwise they're bored and they're not, 5 people for 8 questions seems a little bit excessive. Well, anyway, thank you so much, folks. Enjoy your weekend. And vote for our polls from today. And I will see you on Tuesday. Thank you.